So linear and binary search was actually gone over in Chapter 7. And it is at the end of Chapter 7. It's in searching our arrays. So our most basic data structure is our array. And we saw how we could use array lists to make things better because we didn't have to worry about the size of our array. Does that mean that we still don't use arrays? No, we still use arrays. Okay, you still definitely use arrays. And we still use array lists. So you use array lists and arrays. When would you use one as opposed to the other? That might come in time when you get to decide that, but usually if you have a small amount of data and you don't want to put a lot of abstraction into that data, then you would just use a regular array. Because an array list is a more abstract data type. Okay, you are taking away a lot of how it's actually stored in the computer. You're giving that to the computer. You don't care how it's stored. You're using that array list. It's storing it how it wants to store it. But when you want more control over how things are stored, you would definitely use an array. Okay? And so one of the first algorithms we kind of note or write together is this linear and binary search, and they are used with regular arrays. Okay? And they are gone over in Chapter 7. So the way that a linear search works, it's pretty easy. In fact, I have a little visual here. Let me make another pointer. So let's say we have some values, and now in a linear search, your array does not have to be in any type of order. Okay, order doesn't matter inside of your array. So I could have variables or values in here that aren't in any type of order. Now when I write these values in here, you can think of them as integer values. And you can think of this as just a simple integer array. But note that when we get to more abstract things like objects, what would we comparing inside of this array would not be integer values, but what's called their key value. So if we had an object of type student, okay, we would have an array of student objects, right? Like we've been doing all along in class, right? Making our arrays of objects. If we had an array of student objects, what we're comparing inside of here would be like their student IDs. So we're going to do something pretty simple today. We're just going to have an array of integers just to make sure we know what the algorithm is, but you can take it to another abstraction level and have it be an array of objects. And instead of just regular integer values that you're comparing, you would compare like their keys or their student IDs or employee ID or something to that effect. Okay? All right. But the algorithm will still work the same way. Okay? So just visually, how this thing works is we have an array inside of our computer. A lot of times we draw arrays abstractly like this. Okay? And when you start a linear search, you keep track of the index pointer. So you keep track of a reference to which index you're looking at currently. Okay? And you have a value that you want to find. Let's say we want to find the value like 45. Okay, so this is the value we want to find. So the way the linear search works is you start at index 0. And you check and you look at the value at index 0 and you compare it to the value that you're looking for. And if it is the value that you're looking for, then you say, hey, I found it. Okay, then you can stop looking and you return, usually you return the index of where you found it. You could return a Boolean saying, hey, true, I found it. You could return the actual value. But in the algorithms in the textbook and a lot of algorithms online, they'll return the index of where they found it. Okay? So let's look for a different value. I put a lot of 45s in here for some reason. Now, can you have repeats? Okay, you can designate whether you want repeats or not. But it doesn't really matter if you have repeats. What if you did have a repeat? It would find the first value that matches the one you're trying to find and return that one. Okay, if there was repeats. Let's say I'm looking for the value 122. Okay, so you would keep track of your index and you would start at index 0 and you'd compare 45 to 122. It's not it, so you would increase your index by 1. Look at the value at this index 1. Compare it to what you're looking for. Okay. If it's not the same, then you loop again and you go to the next value and you compare it to that value. Okay. And you keep on going. It's pretty straightforward. It's how we normally look for things. And why do we have to look for things this way in a computer? Yeah, the computer's not that smart, for one. And the reason that it's not that smart is because it's binary. And binary means we can only compare two things at once. And that's the main limitation on a computer, is that it's binary and that it can only compare A to B. It can't compare A to B to C to D to E to F. No, it compares A to B and then that's it. So in all these sorting algorithms, we'll have comparing A to B and then a lot of movement. Okay, but we're not going to get to the sorting algorithms today. And in the searching algorithms, we do constant comparison of the item we're looking for to the item we're currently looking at inside of our array. So you're just comparing, and then when it's true, when you find that item, that's when you stop. And you can say, yes, I found it, and you usually return the index. So I would return number 4. Okay. Let's try to write this algorithm out. Now, much of this class so far has been dedicated to learning object-oriented design and reviewing our arrays. But the main focus of this class is supposed to be on algorithm design. Okay. And the main focus of computer science is algorithm design. So I'm going to write it up here for you. You guys don't have to write it separately. We'll write it together. But let's just practice writing an algorithm. Okay, and we did some algorithm writing inside of our level 1 class. But we need to remember how to write these steps. And there's lots of different ways that you can write algorithms. I like to write them in plain English at first, with some pseudocode kind of mixed in there and some algorithm terminology. Okay? So if I were to write out this algorithm, it's good to have our visual as we're writing out these algorithms. Okay, we can make some assumptions at first. Our assumption is that we have an array, an unordered array. And everyone knows what an unordered array means, that our values are not in any type of order. Now, I actually did write most of the values in order there. That was just on accident. But you can see the 74 there is not in order. Okay, so they're not in any kind of like order. So we have an unordered array. Okay. And so what would be our step 1? Maybe I'll just write 1. So what's our first step that we would do? All right. He says check the first one. So check the value at the first index. At index equals 0. And we want to check the value at index 0, and what do we want to check it for? Check if the value at index 0 is what? At index 0 is what? Equal to the value we're looking for, right? The value we are searching for. And actually, that would be another assumption. We know the value that we're searching for. Okay, so we know the value that we're searching for. So we check if the value at index 0 is equal to the value we are searching for. So we're going to have if it's true or if it's false. Okay, and we can make steps for each of those. So in my step 1.1, I would put if true, then what do we do? If we found the value, like we were searching for, such as if we were searching for number 45. We follow this step, check if the value at index 0 is equal to the value we're searching for. Hey, it is. What do we do then? Then we return the index. The index. So we return the index. And when I say return the index, it means what the index is pointing to here, or the value of our index. Okay. Now, if it's not, what do we do? So let's say we're searching for the number 89 inside of this unordered array. And so we did step 1. We checked if the value at index 0 was what we were searching for. And now this time around it's false. So what do we do? You guys tell me. Huh? Yeah, we increase our index. We move to the next index. Good. Yeah. So we can say something like increase index by 1. And we can even write some pseudocode in here, like index plus plus. Okay? And then what do? We go back up to step 1. And we check to see if the value at that index, now we wrote it a little bit differently. So we shouldn't say at index 0 here if we want to go back up to step 1. And what do we do to our algorithm? We could take out the equals 0, but we want it to start at 0. So we can put that step up here. We could say set index equal to 0. And so then when we say go back up to step 1, we can check if the value at index is equal to the value we are searching for, and it's not going to be reset to 0. Okay, so do you see how we kind of wrote that algorithm? You just start writing it, and then when you need to change it or pull a value out, you pull that value out. Now we know that we're going to go back up to step 1 for a while. So we know that this is going to be a loop. Now we can write this loop a few different ways. Okay. We can make it step 3 and so go back up to step 1, but a lot of times when we write these algorithms, when we realize that we need to repeat these steps for a certain amount of time, we'll make a step above those steps and have it be our loop. Okay? So this would say while, or for, we can even have a for loop because we're in an array, or we can have while. While something, then repeat steps 1 and 2. And so when are we going to stop? So while something, repeat steps 1 and 2. Okay, so we're going to repeat these steps while what is true? Right. Good. Well, index is less than the length of our array. Okay. And so he even said array.length, which is kind of like pseudocode. And he says -1, and that's important because our array length right now will be 6, but our indices are 0 to 5. Okay, so we always do array length -1. If we wanted to, then you could write things like that. Okay, that's kind of like pseudocode. If you wanted to write it in plain English, how would you write that? Well, index is less than the number of elements in our array. Okay, so another way that you could write this, you could say, well, our index is less than the number of elements in the array repeat steps 1 and 2. Now, are there any other criteria when we should stop? Well, we did put well, if we found it, we would want to stop. But because we're going to return the index and actually stop our algorithm right here, we don't have to check for that. Okay? So this is a good algorithm. We set our index to 0, and maybe my step numbers are a little weird, but that's why I hate putting step numbers at first. This one would be 2.1. Wait, no, this would be 3. That's why sometimes I leave the step numbers out till I'm done writing an algorithm. Because my step numbers get messed up. So it says, okay, step 1, set index to 0. That was important. While index is less than the number of elements in our array, repeat steps 3 and 4. Step 3 was check if the value at index is equal to the value we are searching for. And we can draw pictures to visualize this. If it's true, then we return the index. And if it isn't, then we go to step 5, right? Or 4, actually this would be step 4. We increase the index by 1, index plus plus. Okay. Now what step? We need one more step in here. And actually this one, if we were doing our steps right, this would be in our loop. But oh well. Okay. We'll just leave it like that. Step numbering is not as important as getting the steps in the correct order. So our last step, do we need a last step? What if we don't find it? We are going to exit that loop. When this becomes false, when the index finally reaches, let's say we're searching for the number 233. We follow our algorithm and we increase our index and we compare. We increase our index and we compare. So we get to the very end. It'll be false. We increase our index. And now our while loop is false. And we're going to get out of our while loop, right? We're going to get out of that while. So what should we do if we don't find it? You guys remember what the book does and what a lot of algorithms do if they don't find it? Yeah, we return a -1 because a -1 doesn't make sense that that would be an index. So you return something that wouldn't be an index. So a lot of times in these algorithms they'll return -1, and if you are searching for something and you get a -1, it means it hasn't been found. Okay, so we could say the value we were looking for is not found, so return -1. And that would be a nice, well-written algorithm. And we can look at what they wrote in the book and compare it. So here's some code that they wrote in the book, and we're going to use this code today. We're going to do some comparisons. But just to compare it to our algorithm. Okay. Now they used a for loop instead of a while loop, but it's still iterating the same way. From index equals 0, so our step 1 was up here, and their step 1 was inside of their for loop. Here's their loop with their Boolean, I less than list.length. And we did the same thing. Because remember, a for loop can always be a while loop, so it doesn't really matter in your algorithm all that much. Okay. And then they do their comparison right here. If the key equals that current list item at that index, then you return that index. That's what we're doing. We're increasing index by 1 in the for loop up here, I++. And then if we don't find it, they go to our step 5, was return -1. And we can see that our algorithm, how it's written in code. Okay? All right. So I'm assuming that we're good on linear search. All right, and we're going to compare these things. So we're going to do a test after. So remember what linear search is. Now let's go over binary search, and then we'll compare them. All right. So binary search is a more efficient search. Hopefully you read it in your textbook, and they had some diagrams here about binary search. But let's look at a visual for binary search. I debated whether to use these visuals again, and we'll use our Excel visual too to write our algorithm. But let's look at how binary search works. Okay, let's say that this is our array, and instead of horizontal, they just made their array vertical. Okay, but it's still the same thing, kind of how I made it with the the keys are all integers, and then these are our, of course, array indices. Okay, so if we were searching for, let's say, a number inside of this array with binary search, actually, does it let me change binary search nowadays? So these applets are a little aged. So let's see. I think I have to make a new one. No. There we go. Oh, and then we have to fill it. Actually, a student of mine is helping me remake these in JavaScript. If anybody else wants to help. These were done with Java, and these are Java applets. And they're a little hard to run and a little clunky. But I think they serve a good purpose for visualization. Okay. So we have our array here. And this is kind of like our index pointer, kind of like how I had in the Excel spreadsheet. Okay, this little red arrow. It says where we're currently looking at in our array. Okay, let's say we're trying to find this value 12 in our array. And so it doesn't start at index 0. The first value it looks at is right in the middle of the array. Okay, so the way that binary search works is it knows that our array is filled from 0 to number of elements. Okay. And so what it'll do is it'll say 0 plus number of elements divided by 2. And that's the first place it's going to look. It looks right in the middle. Okay. So it looks in the middle and it compares it the same way we did before. Hey, is that the number we're looking for? If it's not, what does it do? Oh, and this is actually very important. I forgot to mention. The most important thing for binary search is that our array is in order. Binary search does not work if your array is out of order. Okay, so it has to work with an ordered array. Okay, so notice that our values are in increasing order. That was very important. All right. So it looks right in the middle. It says, hey, that value is not in our array. Where do you think it's going to look next? Yeah, it looks in the top half. So what it does is it takes that little pointer and it's going to look in the top half of our array. So in other words, it's going to look right in the middle of the top half of our array. Okay, so I'll hit find. It says checking index 5, range from 0 to 11. And now it's checking index 2, range 0 to 4. So it knew it was less than the current value we were looking at, so now it's looking in the front half of our array. Of course, it's not going to find it because 301 does not equal 12. Where is it going to look next? It knows 12 is less than 301. It's going to look in that top half again. Okay, it looks at 203. It knows 12 is less than 203. But now it knows, hey, there's nothing less than 203, and it ends. That was kind of like a fast rundown of how the binary search works. And then we're going to go step by step. We're going to write the algorithm, okay? All right. Because actually, in a lot of interviews, they will actually ask you to write the binary search algorithm by hand on a whiteboard. Okay? And it's not that hard to write. So we're going to write it together today. But just to see how it works, let's say we're looking at something in the top half of our array. Okay, and I'm trying to find it. It's going to look in the middle again, but it's going to see that my number 859 is bigger than the 425 and search in the top half of my array. Okay. It sees the 859 is bigger than 757 and it's going to search in the top half of my array again. And then it finds the 859. So let's go a little bit slower through that and write our algorithm. Now to write this algorithm, we're going to need a couple more pointers. I call them pointers, but they're really just holding the values of our indexes. I called them low, and low is going to start out at 0. Low always starts out at 0. He's going to be our low pointer. And then we're going to have high, and high is always going to be at number of elements. Notice that he is not array.length because we could have some empty spaces inside of our array. So the high pointer always points to the number of elements. So if number of elements is 7, actually he would point to number of elements minus 1. He would point to that index. Because the number of elements in this array is 7, and our high pointer is always going to point to number of elements minus 1. Okay? All right. So let's write this thing. Okay, and I'm going to write it up here, and you guys can just follow along with me and tell me things, okay? So that way you're not just madly typing. You can just concentrate on how this thing is going to be executed, okay? All right. So in our step 0, I'll give this guy to you. We're going to have 2 index pointers, and that's part of our assumption, actually. These are kind of like our variables that we're declaring. We're going to have these index pointers, or variables of type int, that will hold indexes in our array. Okay? And these variables, I just named them low and high. And in a lot of algorithms, they'll name them either beginning or ending, low or high, x or y. Okay? But we're going to set low equal to 0, which is the first index in our array. And then we're going to set high to number of elements minus 1. Which is the last item in our array. Which is the index of the last item in our array. Okay, so that makes sense, right? So whenever you're writing this thing, remember that it's not arrays.length or arrays.length minus 1. It would be number of elements minus 1. And you keep track of how many elements you have in your array. Okay? So if your array is not full, you're not going to be searching those last places in your array. Now we need to search in that middle index. How are we going to know where the middle is? How can you figure out where the middle is? Just knowing those 2 things? Average. Yeah, it's our average, right? It's our high plus low divided by 2. No, actually it's high minus low divided by 2. So it's not really average. And we'll see why it's high minus low divided by 2 as we move on in our algorithm here. Okay. So then we'll set our mid pointer, okay, our mid index pointer, to high minus low divided by 2. Is it plus? Hold on. If you were in 3, it would be, oh yeah, it would be plus, sorry. Because that would make sense, because he was saying, hey, use an example. I always get the minus and plus mixed up. But if we knew that we were going to search right here, it would be 6 plus 3, it would be 9 divided by 2, and that would give us the correct index. Whereas 6 minus 3 would give us the wrong index. Yeah, that is important. So in our algorithm, what is 6 plus 0 divided by 2? 3. So our mid-pointer is going to be right there at index 3. So he's going to equal 3. He's the index at 3. Okay? All right. What would be our next step, do you think? When we find the middle, what did we do in the algorithm? Do you remember? We compared it to what we were searching for. So if we were searching for the number 233, we'd compare 89 to 233. Okay? So we could have an if statement in here, or you could have the word compare. Compare if the value at mid is equal to the value you're searching for. And what if it's the value you're searching for? Return say, hey, we found it. So if it is the value you're searching for, then we just return the index. And what index is it? Mid. So if you found it, then you stop and you just return mid because it means, hey, we found it. So if we were searching for 89, we'd find it in one step and we'd return index 3. Okay? Now if it's not the value we're searching for, what do we do? Now remember that this has to be in order. Dang it. Okay, one side note. So your array has to be in order. And actually we should put that in our assumption. So if it's not the value we're looking for, and we're looking for, let's say, number 233, what would we do? Now this step might be, it was kind of glossed over in that little visual, but you can kind of think what we're going to do. We're going to search in the upper half. Okay? And what we're going to do is we're going to take that low pointer and have it equal mid. Okay? And then we'll repeat the steps of having high plus low divided by 2 and setting mid to that value. Okay. Now if we were searching for a smaller number, let's say we were searching for 45, what would we do? We would take high and move it down to mid. And now high plus low divided by 2 would equal 1. Okay. So here's where we need to have a Boolean check. So compare if the value at mid is greater than the value we're searching for. Okay. So compare if the value at mid is greater than the value we're searching for. If it is, then we move, so if it's greater than the value we're searching for, so the mid is greater than the value we're searching for, then we're going to move high down. Okay, so if the value at mid is greater than the value, say we're searching for that 45, and we just looked at 89. That's what we're doing right now. So we just compared it to 89, and we said, oh, 45 is less than 89. What did we do? We took that high pointer and set it equal to mid. Okay. Then high is set to mid. And you just remember that these are indexes. We can even put index high is set to index mid. Because remember that these are indexes, or indices. Okay. All right. Now, if it's not greater than the value we are searching for, so it's not equal to, it's not greater than, what's the next one? That means it has to be less than. Okay. So this would be the case if we were searching for a big number, like 233. What would we do if we know that this value is less than the value we're searching for? We would move low up to mid. I think it's mid plus 1, but we could still do mid and it would still work. So if it is, if it is, then we do that. And then if it's not, this will be our else part, then index high is set to index, index low then, is set to index mid. So we move that low pointer up here. Now after we move the low pointer up, let's say we're searching for 233, what would we do again? We'd repeat that step. We'd say high plus low divided by 2. What's 6 plus 3 divided by 2? That'd be 9 divided by 2 is 4.5. And what do? We just lop off the decimal. We treat it like integers. Now you could either round up all the time or round down all the time. We're just going to round down all the time or floor it because we're going to treat it like integers. Either way would work as long as you stick to your methodology. Okay? So if we say, hey, we're always going to round down, then 4.5 becomes 4, and we check at index 4. Okay, so do you see how we repeated those steps of high plus low divided by 2? We check at that index. And then we repeat the same steps. 233, the value at this index 4 is less than the value we're searching for, so we move the low pointer up to mid. And we repeat. High plus low, 6 plus 4 divided by 2. We check index 5. We check the value at index 5, 150, and compare it to the value we're searching for, 233. It's less than the value we're searching for, so we move the low index up to mid. And now we'll do 6 plus 5 would be 11 divided by 2 would be 5.5. And actually I wanted this to happen so we could see why we needed to do something different. And so if we round down and we search for 5 again, so 6 plus 5 is 11. 11 divided by 2 is 5.5. Where are we searching again? 5. And then where will we search the next time? Oh no, we have an endless loop. So how could we change our algorithm to make it not do the endless loop? I think if you saw the algorithm in the book, you know. Jason, what do we do? We have to change our low pointer a little bit differently. So when we're searching for these things, where should we set low pointer to? We set them to equal to mid, and we saw that, hey, that led to an error, an endless loop error. Where could we set them to that's similar to mid, but a little bit different and still keep our algorithm? How about mid plus 1? Let's try mid plus 1. If we do mid plus 1, it would be 6 plus 4, it would be 10, divided by 2. It would get here. Okay. And then it wouldn't be 150, so we know we'd have to move the low pointer up again. So we'd move up to 6. And now it would be 6 plus 6 divided by 2, which would be 6. And now we're checking that 189. We only check the value that mid is pointing to. These high and low pointers are only here to keep track of where we're searching in our array. We never check the values at high and low. We only check the value at mid. And high and low are just keeping track of what part of the array we're searching. Okay? But I kind of wanted to do that so then you could see why it's mid plus 1 and not just mid. Oh yeah, so then that would be the end of our algorithm. So if we come to low plus high, and let's say we're still searching for, and we're doing our algorithm with mid plus 1, or not mid plus 1, low equals mid plus 1. So if we searched here and 189 is less than 233, our algorithm says have low This is the low. Equal mid plus 1, and now low is in front of high, and that tells us when to stop. That's our stopping case right there. So that way we can get all the way to the end, and then our stopping case would be when we move that low pointer beyond the high pointer, or the high pointer underneath the low pointer, or low index.
Would you have like a
In fact,
statement to say that it wasn't found in the mix?
yes. So what you would do is, you know, you want to keep on repeating these steps until low becomes greater than high or high becomes less than low. Okay? So it's actually all three of these steps get repeated, or actually more than three, in the sub-steps. 3 main steps and some sub-steps. Get repeated until low becomes greater than high, or high becomes less than low. Okay? So here in our step 0, we could say while high is greater than low, repeat the steps, and once that is violated, meaning once high becomes less than low or low becomes greater than high, then we stop. Okay, so while high is less than low, then we repeat these steps. Repeat steps 1 through 3. Okay. All right, now if this ever becomes false, meaning that the low became bigger than the high, then we'll go on to step 4. And step 4 would be return -1 because the value is not in an array. The value we're searching for is not in the array. All right, and then we need to change it down here. If it is, then index high is set to index mid plus 1. Else the index is low and is set to index -1. And we saw why that was important. Otherwise, we get stuck in an endless loop. Okay, it looks like it's working if you don't put the +1 and -1, but then you can get stuck.
I was wondering what is that in? While would it be need to be greater than or equal to, or is it by
Oh yes, that's important actually. And we'll can see why that's important when we got to that last index here. Yeah, low and high are equal to each other, but high is not greater than low, and that would be a false case, and we need to search that last one. So that was important. So we actually need to put the equal to here. Good, excellent. Everyone kind of saw why we need the equal, otherwise it wouldn't do that last case. And that would lead to logic errors. It would look like it's working most of the time, but when we were searching for something, like at the ends, it wouldn't find it unless we have that equal to right there. Okay? Now, most people don't memorize these things, okay, but you should be able to know how binary search works and be able to write something like this out. And you can write it how we did in steps. And when you're at an interview, they actually like you to draw pictures. Okay, they like to see how your brain works. And if you draw pictures, it's actually a really good thing because it means you think visually. So do draw the pictures like how we had here to remember it, how it works. Okay, and do kind of like how we did here, and then you could write out your algorithm the same way we did. Okay, and you could practice this. In fact, in your homework, I have you practice writing out the steps. Okay, and there are lots of ways that you can write them out. I wrote them out in plain English with some pseudocode, but if you look online at binary search algorithm, they wrote it out a little bit more in pseudocode. So it's even more so in pseudocode. Okay. But the steps are still the same. Okay, just to review our steps, lower bound equals 1 and upper bound equals number of elements. Now they put 1 because in the programming language or whatever they're using for, they just mean the first index. So some programming languages use 1 as their first index, like Maple. Okay? But no, it's the same algorithm. Even though we didn't put a 0 here, we just mean the first index. So start lower bound or low at the beginning and upper bound at the other side, number of elements. While you're not finding it, notice that they just put a check here. If upper bound is less than lower bound, then they exit and they say, hey, it's not found. So they wrote it a little bit differently, but it still does the same thing. They set their midpoint to lower bound plus upper bound divided by 2. Now they set it to lower bound plus upper bound minus lower bound divided by 2. No, it seems a little weird. We could try changing our code to see if this works. If it's, less than what's at the value at the midpoint, then we set our lower bound to midpoint plus 1. And if the value we're searching for is greater than what we're looking at currently, the value we're looking at currently in the array, then we set the upper bound to midpoint minus 1. So we draw the upper bound down. And if if the value we're looking for is equal to what we're currently at, the point we're currently at in our array, then we found it. But I encourage you to look at different ways that people have written this algorithm online. Maybe some of those will actually, make more sense to you. So what I was going to have us do is actually write out this code. And we could look in our book at this code, actually. Let's take a look at how they wrote it. It's actually written pretty easy here. Actually, this code is kind of hard to read because he's small. Can you guys read that? I'll highlight them. Dang it. How do I unhighlight? Oh, wow. Well, anyways, so they have this code here. They have a method. Okay. And so they have the low pointer, and it's set to 0, and then the high pointer is list.length minus 1. Now, what is this assuming? This is assuming that our entire list is full, because remember that if it wasn't full, we'd want number of elements minus 1. Okay, that's important. They set the mid-pointer to low plus high divided by 2, and they check to see if the value they're looking for is less than the value at that index. And if it is, it sets high to mid minus 1. Otherwise, it checks to see if they found the key, and then they return it. Otherwise, low equals mid plus 1. Now, does the order of these steps matter? Now, writing these steps in different order might make it more efficient and less efficient. But to tell you the truth, well, we can test this and we can see if it's more efficient or less efficient. And then in the version 2, they put that while loop around their logic. And they say, well, high is less than low, then repeat those steps, just like how we wrote our steps. All right. Now, you can either copy and paste this, or we could use, I guess we could just write it out too. What we're going to do is we're going to write these two methods for linear search and binary search, and then we're going to give them an array, and we are going to count the number of steps each search takes. And I know we haven't gotten to big O, but we're going to start talking about what's called big O. Okay, or order of. How do you compare one algorithm to another? So this is two different algorithms we're using to find something into an array. Okay? And we can tell right away, hopefully you can tell, that binary search is more efficient than linear search. And why do you think binary search is more efficient than linear search? Well, linear, we have to check everything. In binary search, we're halving it each time. So hopefully it's obvious to you that binary search is a more efficient search than linear search, and is going to take less steps to find something with binary search than opposed to linear search. That means that binary search is more efficient than linear search, and that when we want to make our programs run better and faster, we should always use the more efficient algorithm. Okay? So for like 100 items, it doesn't really matter, right? You can use linear search, binary search, 1,000 items. When you get up to millions of items, hundreds of millions of items, the amount of steps that each of these searches take can have a drastic effect on how your program and how long your program is running. It could be days as opposed to hours, or it could be hours as opposed to minutes. Okay? And I actually have people test code in here that did actually take days to run. Okay? But, yeah. Right? Because it's fun to do that, right? We see how fast our computers are, and if it's taking it days to run, how many steps it actually really is. Okay? So what I thought we'd do is actually count the number of steps it takes to find something in both of these algorithms. Okay, so we just fill up some arrays, search for the same value, and count the number of steps so that we can compare these things. So when we compare two separate algorithms and we're counting their steps, it's called big O analysis. Because how do you compare one algorithm to another? You count the number of steps it takes for this algorithm to run and the number of steps it takes this algorithm to run. Okay? All right. So I do want you guys to do this part. So you guys can do this part. So we're going to write out our algorithms in code and then count their steps. And we'll try just writing our code without even looking at the other code. We'll use it with our algorithms. And actually, let me upload these algorithms then to Blackboard. Well, I guess you guys can look up here. Should I upload them right now? Okay. So these are the algorithms we wrote together. I'll put them right now inside of Blackboard. Oh, I named them bad. Okay, and I'll put them into our Blackboard in our class assignment. So I did make a class assignment for today. It is good practice to try to write out these algorithms in code. Okay. So this will be our searches, our simple searches. And we'll go ahead and write a test class. I'm going to call it testing searching, but you can call it whatever you want. I don't mind. Just always follow the rule of capitalizing your class name. We'll go ahead and have main in here. We're just going to kind of test our simple sorts, or not sorts, simple searches, our searching, our linear and our binary search. So we'll just write them as, we can write them as static methods if we want. Now just remember that a static method is one that does not use instance variables, so we'll have to send it the array, and we'll have to send it the key that we're searching for. So it's going to be kind of like the methods that were written in the textbook, actually. Okay. Now we do want it to return the index of where it found this item in the array, or -1 if it didn't, so our return type will be int. Okay. And we can call it linear search. We'll do linear search first, and we'll see if you guys can do binary search. Now we are going to take some parameters because he's static. We're going to send to him the array that we're searching for. And then we'll give him the key that we're searching for. So whatever value we're searching for, usually they call it the key. Okay. But that's like the value that we're searching for inside of our array. All right, so using our algorithm, first thing we want to do is set our index to 0. Now this is our searching index. So we can set index to 0. And then looking at our algorithm, it says it has a while loop. Now you can have a while or a for loop, remember. But since we wrote our algorithm with a while loop, let's go ahead and use a while loop. While index is less than the number of elements in the array, repeat steps 3 and 4. Okay, so we can say while index is less than the number of elements in my array. Now, how many elements do I have in my array? Now, inside of the book, they always fill up the array totally. They fill it up. And so then they just do array.length. I think we should tell it how many elements we have in our array. So let's go ahead and give it another parameter. And we'll call it num of elements. And the reason this is because sometimes we don't fill our arrays totally, and we should recognize that. Okay, if our array is not filled totally up, this is how many elements we have inside of our array. Okay, so while our index is less than the number of elements, we're going to perform those steps that we said that we were going to take. Looking at that, again, our algorithm, it says repeat steps 3 and 4. Step 3 was check if the value at index is equal to the value we are searching for. So we do a simple check. If the value at index equals what we're searching for. If true, then we return that index. So we just say, hey, we'll return our index. Otherwise, we go to step 4, and step 4 was increase the index by 1 with index plus plus. Now, if you were writing this code and you recognized, hey, I have index 0, index less than num elements, index plus plus, hey, I could convert that to a for loop. You could convert it to a for loop. But remember that for loops and while loops are comparable and the same. when you compile them, so you could leave it a while loop too. Okay? But if you made it into a for loop, it would be just like your text. Now we still have that last step we need to write. And our last step was outside of our while loop or after that while step there. And it says the value we are looking for is not found, so return -1. So outside of our while loop, after we've done searching and if we never found it and we never returned, that means that our index is now equal to the number of elements, because this is going to be false if we ever get down here. Then we return that -1. All right. I was debating whether to write our binary search first and then write the test code, or test code binary search, but I think we'll write our test code to show you how we're going to test this thing. And then I'll let you guys kind of write the binary search and do the same. Okay? All right. So to test this thing, we're going to have to make an array. Now the array does not have to be in order. Okay, but for binary search it does have to be in order. Now does it matter if this inside of a linear search is in order? No. So I thought we could just make our test array in order. That way it'll work for both of them, and we can test the two searches with the same array. Okay? So let's make a test array. Okay. So we're going to create a test array. Create a test array. And we'll go ahead and put it in order. Well, not put in order. We'll just make it in order. So that way he'll be inside of some kind of order, so he'll work for both our binary and our linear search. So how do you create an array and fill it? So we're going to make it an integer array, just because it's easier. And later on we can do this with objects. Actually on Wednesday we can do it with objects, and it works the same way. We just use their IDs, remember. Okay. I'm gonna just give it the name numArray. Okay. And he can equal a new integer array of size. Or I can just put in a size. Now we can change this number to bigger or smaller and see how our code runs differently. Okay. Which relates to our big O analysis. So for now, we can just make it size 10, and that's fine. And then we'll start growing it and see how our algorithm works. Our algorithms. Now we want to fill it. So we're going to go ahead and fill this array with some values, some test values. Now, this is why I wanted to make that constant size. Maybe we will make a constant size. So then we don't have to keep on writing him. Okay. And this will be I++. And so let's fill this array. We'll just say numArray at index I will equal, what if I just went ahead and filled them up with the numbers 0 through 1,000? 0 through 10. And this is just for a test array. So note that the numbers are in order, and they're just the numbers 0 through 9, actually, that are going to be put into this array if I make them size 10. But that's okay for what we're doing. Okay. Now I want to count the number of steps. So I'm going to call my method. My method was called linear search. And my method takes in an array as its first parameter. The second parameter was the number of elements or values that he contains, and he actually contains size of them. And then The last parameter was the key that we're searching for, and what should we search for? First time around, let's set our key equal to something that's in the array. And actually, I'm going to go ahead and make a variable up here. Okay, and I gave him a long name, but let's go ahead and search for the number 5 or something. Now it's going to return an integer to us. This method's going to return an integer if it finds what we're looking for. Otherwise, it returns a -1. All right, so we want to count the number of steps inside of our linear search. Okay. So I'm going to come up here to my method, and I'm going to modify my method and just make a little counter in here that's going to count those steps. Okay. So the code I'm writing now is only for us to test. And I'm going to call it the count steps method. And so the steps I'm talking about are the algorithm steps. So here's our steps here. Okay. How many times are we executing this while loop? How many times are we comparing, okay, making this comparison here? Comparisons in a computer take time. And so if we can count the number of comparisons that we're making, we can count the steps it's a way of counting our steps and comparing our algorithms. We can compare the number of comparisons each algorithm makes. Okay, so we'll compare the number of comparisons that our linear search is making to the number of steps the binary search is making. Okay, so we'll have this variable we'll call count steps, and every time I get into my loop, I've made one comparison right here, and so I'll increase my count steps by 1. Well, actually, it'll be this comparison that I'm counting, actually. But every time I get to this part in my code, I am making this comparison where I'm comparing my key to the value in my index. Okay. And I'm going to count how many comparisons I'm making. Okay. All right, now I'm debating whether we change our algorithm or we just system out print line our steps. Let's just system out print line our steps. So we'll just output the number of steps, and we'll say the number of steps for linear search is, and since this is just test code, that's why I put a system out print line in this method. And then we'll just output the number of our steps. Now note that I put this output outside of the while loop, so after the work was completed, so it knows how many steps it took. Okay, it either found it or didn't find it. Actually, if it doesn't find it, it actually won't print out the number of steps. So I'm going to copy that line of code and put it right here as well. And do you see why I have to put it right here as well? Because if it does find the key, I still want it to print out the number of steps. And then if it doesn't find the key, it'll come down here and print out the number of steps. So either way, whether we find the key or not find the key, I still want it to print the number of steps. So then we can compare these things. So everybody kind of got that, right? So we printed out our number of steps. So in testing the linear search, We're going to make this array. We're going to send that array to our linear search method. He's going to print out our number of steps. So we know we're filling our array with the numbers 0 through 9. So our array is going to look like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 because we just used a simple for loop to fill up our array. So I'm going to search for the first value in my array. And how many steps should that take me? If I were to run this thing, it should tell me how many steps there are. And how many steps does that take? 1. That's the best case scenario for a linear search. Best case scenario in a linear search is the first item you're looking for. It takes 1 step, very efficient. Hey, 1 step is like gold, right? Yeah. In big O analysis, having 1 step is like the best you can do. Okay? But that was for the first item in our list. How about if we search for the last item in our list? What if we search for a 9? How many steps should that take us? If we search for the last item in our array, it should take us the number of elements, okay, long to search for that item in our array. So notice that our search number of steps is 10. This is the worst case scenario. We're searching for the last thing in the array. You can think, hey, that's the worst case scenario that you could have. Okay? So if I were to tell somebody the average number of steps that it would take to find something in a linear search, what would I say? If the best case is 1 and the worst case is 10, what's the average? What do you think the average is? What's the average of 10 and 1? You guys tell me. Yeah, 5. Okay, 5.5 or about 5 steps. Okay? And so this tells us about a linear search. The worst case, total number of elements is the number of steps it takes to find something. Best case, 1 step. The average case is n divided by 2, the number of elements divided by 2. And that's actually its big O time. So we like to describe our algorithms and what's the average number of time to find something. And for a linear search, this is how you would write it. Okay. It takes on average n divided by 2 steps to find something in a linear search. So our linear search algorithm is big O n divided by 2. Because that's the average of how long it takes to find something using a linear search. Okay, so if it was 1,000,000 items, how long would it take to find something on average? 500 million steps. Okay, if it was 1,000,000,000 items, it would take 500 million steps. Okay, which is not that great for large numbers, right? For small numbers of n, it's okay. Okay, but for large numbers of n, it's not. Now I'm just counting the steps, and those steps equate to time in your computer. So counting steps is just one way to compare an algorithm to another algorithm. You could actually use a timer too. And in fact, in our simple sorts, we'll use an actual timer and see the physical time that it takes. Douglas? Now remember that this linear search is in your textbook as well, and you could use the same linear search that was in your textbook. Linear search should be pretty easy for you to write. Okay, because remember that you're just using a loop to go through that array. You could have used a for loop or a while loop, how we used here. Okay. So these 3 things would be the parts of your for loop. You could also make this into a for loop. Okay. Actually, not this index. All right. Let's do the same thing with our binary search. So I was going to have you guys write out the binary search. Now you can use the code from your book and you could write it the same way, but I want you to try to practice writing the binary search without looking at your book, and then if you need to, I can come around and help, or you can look at your textbook. But just try to write binary search out in code. You have the algorithm right here. You can use the algorithm, or try to remember your algorithm. Okay, I gave you guys this algorithm. And you can work together on this, actually. So if you wanted to work with a partner, actually, you can work with a partner. But try to write out binary search without looking at the textbook or code online. It's good practice. Okay? So just remember the header of your method will look like this. We want the header of our method to be static. We'll have it be static. And then we'll have it return an integer. It'll be the index, okay, if it finds it, and then -1 if it doesn't. We can have the same parameters that we did before for our linear search. So your binary search parameters will look like this, where you're taking the array, you're taking in the number of elements that the array has in it, and then you're taking in the key, which is the value you're trying to find. And remember that it returns -1 if it doesn't find it. Okay? I thought this would be good practice today. So just try writing out your binary search with just the algorithm. See if you can do it. Okay? And then you can double check yourself, of course, or have a partner check you to see if you're doing it right. But it is good practice. Like I said, in those interviews, they'll ask you to write out the binary search on a whiteboard. So it's good to know this algorithm. Okay. You can look at our algorithm as you're writing your code, that PDF I uploaded. Okay. Or even look at our visual as you write your code. But see if you can write your binary search and then put that stepping code in there. Not the stepping, the counting steps code. So after you get your binary search written, you'll want to count the steps as well. And then you can guess what we're going to do. We're going to search then for our binary search, you know, the first item in our array, the last item in our array, the middle item in our array, and figure out how it compares to our linear search. Okay. It's a good place to pause the video.